A twin-engine 767 departs Boston for Paris. 3,000 miles of open Atlantic, no land for 2 hours. 30 years ago, this flight would have been illegal. Today, twins dominate long-haul. What changed wasn't the ocean, but until 1985 that flight was illegal. The 60-minute rule, written in 1953, assumed one engine could quit at any moment. You needed spares and you needed land close. The North Atlantic, 5 hours wide, belonged to 3 and 4 engine jets. More engines meant more fuel, more weight, brutal economics. The alternative was ditching in 40-degree water. So Boeing and Pratt & Whitney made a bet in the early 1980s. New high-bypass turbofans could run tens of thousands of hours between failures. They proposed a deal to the FAA. Let us prove it. Demonstrate reliability below 1 shutdown per 20,000 engine hours, and let twins fly further from land. The program, ETOPS. Pilots called it engines turn or passengers swim. Here's what proof looked like. The standard, published in 1985, not more than 0.05 shutdowns per 1,000 flight hours. That's 1 per 20,000 hours, per engine. For a twin, the odds of losing both simultaneously became 1 in 400 million flight hours. The test wasn't theoretical. Fly the engines, log the hours, count the failures. And the engines passed. Boeing and the engine makers accumulated millions of flight hours. They tracked every shutdown. Bird strikes, compressor stalls, fuel contamination, bearing failures. The numbers came in. The JT9D hit the target, then the CF6, then the PW 4000. In 1985, the FAA granted the first ETOPS approval, 120 minutes for the 767. You could now fly 2 hours from the nearest runway, which opened the door to longer routes. ETOPS 120 in 1985, ETOPS 180 by 1989, ETOPS 207 in the mid-90s, opening polar routes. Today, the 787 and A350 are certified for ETOPS 330, 5.5 hours from land, backed by shutdown rates now in the single digits per million flight hours. Modern turbofans fail so rarely, the models struggle to predict the next event. But how did reliability improve that much? 3 things. Materials. Single crystal turbine blades surviving 1500-degree gas. Redundancy. Dual-channel computers. Backup pumps. Sensors cross-checking sensors. And third, the silent revolution. Predictive maintenance. Every engine transmits real-time data to the ground. Algorithms compare each flight to baseline. A bearing starting to wear shows up as a half-degree temperature rise 3,000 hours before it fails. Which means most shutdowns today aren't failures. They're precautionary. A sensor detects an anomaly, the crew shuts down the engine, the aircraft diverts, and maintenance finds a cracked fuel line that would have failed in 50 hours. The engine never lost thrust. The system worked. That's why the shutdown rate keeps falling even as the fleet grows. We're catching problems before they become emergencies. So what still goes wrong? Failure modes that still matter. Bird strikes can destroy a fan stage. Ask US Airways 1549. Volcanic ash can flame out every engine. British Airways 9, 1982. Ice crystals at altitude can choke the core. A 707 on approach to Heathrow, 2008. But these aren't reliability problems. They're environmental hazards. The industry learned to route around them. The engine itself has become almost boringly reliable. That's why the twin over the Atlantic isn't a gamble. It's 40 years of data, material science, and operational discipline. Engines that report their own health. Maintenance that fixes problems before they happen. Certification that demands proof, not promises. The 60-minute rule assumed engines would fail. ETOPS proved they almost never do. And that's why your flight tonight, 3,000 miles of ocean, has 2 engines, because 2 is enough.